Welcome to another GCBASIC tutorial for the 16F175 chip family. Part 19, Assembly, Alternative Assemblers and Debugging. I have waited over 1 month to make this video for a very particular reason. We are now in 2026 and I can share with you some new capability. This is the very first tutorial video on the new 2026 GCStudio capabilities. So what have we got? We've got a chip, and I'm going to go straight into it. Like and subscribe. You don't get these capabilities from people like Angel and myself without liking and subscribing. It's absolutely required now. So, number 19, assembly, alternative, assemblers, and debugging. I'm going to show you something that is a game changer with respect to that capability in our language. So, let's just recap. GCBASIC open source compiler for PIC, AVR, and LGTs, and it supports this new chip family. And it is a cross-platform with common code translation, which basically means what I'm showing you here in Windows, you can do in Linux or Apple. Just do it. Not a problem. Okay. We need to look at a diagram like this to explain what's going to happen. For the core compiler, essentially takes your source code and generates a hex file. So let me just bring up my pen. It takes your source code and takes it through something that's called a preprocessor. Well, there are some libraries it might need, and it sucks those in. Goes through what's called a code translator, which normalizes things so that it is prepared for the assembly process. And as you go through the code translation, it works out whether it's an AVR, 8-bit PIC, LGT. It does all that stuff at that point. Very intelligent. It then assembles your code. And at that point, it will write some reports out, which you're going to go and have a look on the assembly file. And it's an assembly file that is specific to the chip that you have selected and the target architecture that you're going into, PIC, AVR, etc. Then within the core compiler, it will then link that together and it will produce a hex file. In the linker, it works out where to put your assembly in the hex file. So it, in memory, for that particular chip, works it all out and puts it out. And at this point, you get a file that you can program. That is the core compiler. That was as it was in 2005, has not changed. Let's be quite frank, there's a lot more richness going on, but that is the basic architecture. But what you've got is a number of different options now. You can pass certain things at certain points out to other toolchains. And that has a huge advantage. One, it ensures that the assembly that's been generated by GCBASIC is valid, but it also lets you do other things like debugging, etc. So let's look what happens. Bring up my pen again. Is my pen active? Where is my pen? Takes your source code into the preprocessor, no change there. Into the code translator, no change. Assembly writes out a target file. Now, at this point, things get different because it's written out what should be a valid assembly file here in this green output file. It should have done what it has, and it will create a file. You can then push that into a linker to generate the hex file, and it can be PIC-AS, MPASM, legacy chips only, MPLAB IDE. You can push it out to that. GPASM, AVRASM too. There is validity in doing that. And I'm going to show you one of the reasons why. So, if I was doing this lab in 2025, we would have to take the GCStudio installation and we would have to go and install a whole load of other chains. A lot more. I'd have to go and install MPLabX. I'd have to create a program in MPLabX. I'd have to create that project and make many changes to the environment to make it all work. And then I could actually debug my program, because that's what I'm trying to show you. Now, one of the reasons you might want to debug, but it's now 2026. It's post 2025. And what I'm going to show you is we're going to review a simple LED program. We don't even need to do that step. So let me make it very clear what we're doing. I am going to come out of PowerPoint Live, discard that. I'm going to take that out. I don't even have to do that because it's simple as that. I am going to, just tidy up my presentation. There we go. And I'm going to do that, which is review a simple LED program, start GCCODE, pick a debugger, and we're just going to walk the code. It's as simple as that. And the reason we're doing that, I've shown you that diagram previously, is because we're actually going to leverage something outside, which has been recently developed. So let's go there now. I'm going to go out to a remote machine. I'm on a different computer here, but I need to be on there because it's got the new capabilities. I'm going to open up GCStudio exactly as I have previously. I have not got MP Lab installed. That's absolutely crucial that you understand. I've just installed the new version of GCStudio. And here we go. I can show you the difference is that there's a thing called Package Manager at the top. And in the Package Manager, I've selected some packages and I've installed, I've selected PIC116F175xx and I've selected the 8-bit packages. Because you can do this now way beyond what GCBASIC does. When you see this working, you're going to be stunned. So I'm going to change my programmer. Well, that's really complicated, isn't it, and dangerous, but we're not going to be that bothered. Watch this. Close that down. So you know when you're in this new tool because you have this thing called Package Manager. So I'm going to, exactly the same GCStudio, I'm going to open up my project, and it happens to be a project that's in this folder. It's a project. At the moment, we have to create a project. So I'm in the GCCODE, no different than before. Let me open up a program, and here's my demo program. I'll just shut that down by Control B, and here it is. Here's my program. It's for a 16F175xx option explicit. We have seen all that before. So what have I got out on my desktop? I've got out on my desktop the standard layout that we've had before, but this time I'm going to take my trusty PIC116 Plus, put that aside, and I've got a PIC116F4. And we all know that using a PIC116F4 is extremely difficult and very hard, but I'm going to show you how easy it is. GCBASIC is meant to be easy. This is going to be easy. Okay, so I'm going to debug my program. And rather than use the whole of GC as a GCBASIC, I'm going to actually pass out some of that code, but we're going to present it in this debugger. Now, I'm going to have to lose the camera at some point. Maybe I can move the camera away. It's in the wrong position. I'm going to have to come out and turn off that camera occasionally. But let's just turn off the desk cam to start with. There we go. So we're going to compile that up, function key F6. It's going to flash an LED on port C.1, and I'm now going to compile it. It compiles it exactly the same as it did previously. This is build 551. Anything later than 551 you should be looking at, and it just built it. So what's different? Watch this. No MP Lab. I'm press this little triangle on the left, and it's called, or I could take the restart debugging. The moment I press that start debugging, it then rebuilds the code. It then creates an ELF file, which is actually the debugging file that we require. It puts it into a build direction. What's different about the user interface now is I've got this new interface at the top with GCBASIC debug showing and my program name. At the bottom left, I've got GCBASIC in blue, and now it's gone orange. Well, amber. Ugh. It says different things. I've got new user interface on the left here. I've got variables. What's in the variables? I can look in here. I can see different capabilities. Let me just press function key F11. And now I'm in the source code. I'm in the source code that's been generated by GCBASIC, but I'm in the debugger. I can look at the CPU registers for this particular chip. I can look at the variables that have been created. I can look at the hardware information. I can look at some watch, which I've got set up, and I've got my stack. Unbelievable. Watch this. I'm just going to run it by pressing function key F5, and I'm going to bring up the camera. And we have an LED that's flashing. There was no mystery with respect to programming it. There was no MP Lab or MPE, IPE. We have pushed it directly into the PIC kit. And we can do the same with many, many different programmers. But as you'll find out, that is where we're going to head. Let me just stop the program. I'm going to hide the camera, press the pause button in this new debugger, because I've got some extra capabilities. I've got capabilities that I can single step through the program. As we single step through this program, I will show you that on the camera. So here is the essential program. Let me Control B to get rid of the left-hand side at the moment. I'm setting the pin on, and I'm setting the pin off here. So why don't I just set some debug, not debug, set some program stops so I can see that happening. So watch this, look. Red button, and I've just enabled 2 stops. Now, how do I show you that? Watch. In here, at the bottom, my screen is extremely busy. Breakpoints. I've added 2 breakpoints at those particular lines. So if I run the program by pressing function key F5, and then I'm going to bring up the camera. I might have to shift the camera about here. I'm going to have to shift the camera. Here we go. So this is bit clear. The LED is currently on. In my program at line 109, I'm going to press function key F11, which is a single step in any debugger. If I did it in the IDE, that'd be better. There we go. I can see my watch statements change, but I see the debugger, I see the actual physical LED change. I'm going to run the program, function key F5, it will stop at my next breakpoint. Function key F11, BSF, lat C, comma 1. What does that mean? Turn the LED on. Function key F5, it waits for 1 second. What's the next control? At 109, bit clear, lat C, comma 1, bit 1. Turn it off. You might not like the ASM that we've generated. You can't change it, I'll be quite frank, but you can walk the code. You can see the variables. And there is some extremely great capability in here that you cannot do in other debuggers. Let me stop the program to show you. I've stopped the program. I'm going to get rid of the camera. And now I'm going to go into my source program. Here's my source program. I'm going to dimension a variable. And I'm going to call that my byte as a byte. Equals 1. Now, I'm showing you some new capabilities here. You can assign variables like this now in the new version, in 2026 version. Dim, my word as word equals 2. Actually, let's be quite frank. A word is, what's a word? What's a 256? That will force it. That will show you. Dim, my single as single, single. -1. Can I put -1 in there? Will that work? Let's see if that works. Function key F6, compile. Invalid type. Function key F4, just change my preferences to enable singles. I have enable single support. I failed to set that up. That's not a problem. I just recompile, and I've just turned on single support. There is a reason for that. One day I'll explain. And it's just recompiled it. So how do we know what it's done? How do we know? Well, why don't we just try debugging it? So I've got this little icon at the top now because I've got my, if I go into this triangle, run and debug, I get to see this little icon here. I can press that And now it's going to recompile the whole program with these variables, and it's going to initialize the variables, and we're going to look at it initializing the variables, and it will show you things that you could not have seen before. It would have been extremely difficult to understand this, even in an MP lab. I'll show you these variables being defined and managed, properly managed. It's currently programming it, and we've stopped. We've stopped in the program because I have set this up. I'm not going to show you all that setup. There's too much to show you. So in here, I've got my source code dimension, a byte as 1, and we can see quite clearly that it's going to move like a constant into the W and put that into a variable called m byte. Let's run the program to that. I have run the code to that level. What I can do, I can look at the program variables. I'm just going to get rid of the breakpoints and everything else, okay? Program variables and aliases. And in here, I can see there's something called my byte. It's got an address. It tells you where it is in physical memory. And if I press function key F11, if I look at that memory address, let me just check that. I'm learning this as much as you are learning it. This is all very new. It says here that the value of here we go, the address is set, and it's just set that to 1. That's really clever. Well, let's get rid of the watches because we can see it in here. You can't do this in any other language, what I'm going to show you next. It's going to set the my word to 256. If I press function key F11, it clears the low byte, it sets the high byte. Well, in here, it quite clearly interpreted, as you can see, my word is equal to 256, but it's got a little arrow on it. Open it up, I can see the construct of that. I can see the construct. So I know that it's 256, the low byte is set here, and it's cleared the word variable. Right. Let's look at my single. My single has not been, there's not a valid number in my single. But to use a single, to see this, F11, I'm just setting it up. I'm expecting to see -1 in here because this debugger reconstructs the values correctly using the correct format to put it into something that is man-readable and man-understandable. The only other way of understanding all this would be to go into the calculator. I'll show you this. Function key F4, calculator. If I could spell calculator. It's opening up the calculator. And if I put the values that were actually used just to construct, if I look at -1 in here, put -1 in here and convert, it says it would have to set some bytes, and those bytes would be 191, 128, 00, and it's exactly what we've seen in here, which is clear. So we can see that we're getting 191, 128, 00. We can see that in our source code up here as well. We can see that in the debugger. The values 191, 128, 00 in IEEE equates to -1. You can see the variable build. You can't do that in any other debugger that I'm aware of. And I know you can't do it in MPLAB. Run the program. It's now running. Let's bring up the desk cam. And it's flashing every second. That is enough for this video. What you've got is a capability of debugging and programming, and we support every microchip programmer. I think we're going to be able to do absolutely everything. They are different levels of capabilities. The core compiler will come with just a simulator. You'll always be going to MPLAB and use the MPLAB toolchain. We're fully going to support that forever. Absolutely right. And then we're going to release another product, an add-on product that allows you then to do what I'm showing you here. This is terrific capabilities. So I wanted to show you the debug to walk the code. I've shown you, oh, I'll get rid of that camera. Get rid of the camera. Source code variables and registers. That's why you need to understand the architecture, but it's much more simpler now. There is no MPLAB involved at all. So next I will summarize everything up, and do enjoy.